Hello class, here's our presentation for our final project, stateless full node. We will introduce the topic from 4 aspects. First, stateless full node and Akiva node. Original network with full nodes storing all the UTXO sets is redundant and costly. Adding an Akiva node into the network, which takes the role of maintaining the UTXO sets, helps release the memory of every other node. We also add witness prime number pair into transaction input. Full nodes store state witness which only relates to themselves in order to verify generated transactions as well as calculate balance for each client, and they could communicate with Akiva node for recipients when verifying blocks.
In our Akiva node, we let it to generate initial state and witness in ECE and broadcast it to the network. We store the state witness in the ECE accumulator. In this new state witness, we store a state-like structure. Akiva node stores the whole states in order to provide all transaction witnesses and accumulator proof, so that each node can verify all transactions in their local storage without the knowledge of all states. When an Akiva node receives a block, it will add it to its own blockchain and update the UTXO sets. Then it will update and broadcast the witness to all stateless full nodes.
We use ECE accumulator instead of Merkle tree for state witness implementation, as it can be more efficient. First, we need to choose a modulus n, which is the product of two secret primes, and we need a hash function to map our elements to primes. Then we initialize the accumulator with the initial base g, so we can add something to the accumulator by raising the current accumulator to the value we get from the hash function. To prove the membership, we just need the value of the element and the witness. The exponential part of the witness is the product of all the values in the accumulator except the value being proven. To prove the non-membership, we need to use Bezold coefficients to prove that the element and the product of all elements in the set are co-prime. Aggregating and batching makes the ECE accumulator more efficient. Aggregating means combining many proofs in one constant size proof. Batching means verifying many proofs at once. However, the exponential calculation will be expensive and it's hard to transmit such large values. Therefore, we can use ni-poke2 to prove that we have the cofactor but not necessarily do the expensive calculations.
Welcome back to our group project demo. Our project is based on midterm project, which is based on UTXO. We have implemented 3 stateless full nodes and 1 Akiva node for presentation. We let 3 full nodes connected to the Akiva node. Now, let's get started. I will let the system run for a while and stop it to see what everything is going on. Okay, now we can see that the tip of each blockchains are exactly the same. We can check for a few blocks to prove the system actually works. So, let's go to the very first block. We can see that the node A mined the first block, and all the other nodes received the block after that. Our state witnesses only get updated when the Akiva node received a new block and broadcasted the updated states and proofs. The verification can be done locally for each node because we store state witnesses in each transaction, and each node can do the verification with a crypto proof generated from the Akiva node. We can also check the 10th block for that. Right now, our implementation has some drawbacks such as the efficiency of the verification or the exponentiation computation. We can use batch verification to solve the problem of the verification to verify the transactions in a block in a constant time complexity. Also, we can use ni-poke2 to do the verification without calculating the whole exponentiation. At last, if we have enough time, we can do the comparison between the RSA accumulator and the tree-based accumulators such as MPT. This is the end of our presentation. Thank you for watching.